Okay, we are going to look at Riemann sums, but I'm going to break this down a bit into basic area. Okay, there are formulas provided, and I wrote those formulas right here. There are different forms of them, and they explain what this xi is, and it depends on a left, a right, and a mid. But let's start with the basics. Area under a curve. Okay. We are almost taking a step backwards because previously we have done integration, right? We've done antiderivatives, we've done definite integrals, and if I wanted the area under this curve, x squared plus 3, bounded from 1 to 9, I could simply do the integral, right, from 1 to 9, x squared plus 3 dx. So why even investigate this Riemann sums? Well, two reasons. One, it's the foundation of how this definite integral actually works. Second, it's because some functions out there you actually cannot do the integral of. Okay, we have to use technology, and we may even need to utilize technology based on Riemann sums. And Excel actually has a program to do this, but I'm doing a basic one to demonstrate this idea here, all right? So first, let's see what this exact area would be. Integrate this, we'd have x cubed over 3 plus 3x, range it from 1 to 9. Right, so substitute 9 would have 9 to the third over 3 plus 3 times 9. That's, f of b minus f of a. Substitute 1. 1 to the third over 3 plus 3 times 1. Okay. So 9 to the third is 729 over 3 plus 27 minus a third. I'm going to go in and just distribute. I'm hoping that, which it doesn't look like, but I was hoping that one of these would cancel the fractions. Subtract 3. All right, 729 over 3 is 243. Plus 27, well, 27 minus 3, go in 24 minus a third. Right. Anyways, you get the point. Really from this point forward is arithmetic. 267 minus a third, so without making an LCD, 266 and 2/3. And of course we would probably want improper, or if it's word problem, a decimal, whatever. Okay. We know this is exact. Again, I could write some random function up here that we actually couldn't do the definite integral, and we may end up using Riemann sums. Riemann sums, instead of relying on this formula, it's much easier to use a picture. This is not going to be to scale because I'm ranging up to 9, so if I substitute in 9, my right endpoint would be 9 squared, 81 plus 3 is 84. Okay, I can't get that accurate without graph paper up to 84 here. And the lower bound of 1, I know I'm going to have 4. Also, I'm not doing accuracy here because I want to draw these in. Okay, and x squared plus 3, we know it's a parabola, right? And it opens up and it got shifted up 3. Let me fill in one more point here. Let's say 5. 5 squared, 25 plus 3, 28. We'll say that's somewhere around here. Again, not to scale. I know this would be a parabola and it would be much steeper, something like that. All right. And it crosses at 3. I don't really need that though, because what we're doing is finding the area here, right, contained within that. Okay, a left point approximation using full rectangles. So what that is saying is, first off, split up from 1 to 9 into 4. I could visualize that by going every 2, right? Here's a rectangle, here's a rectangle, here's a rectangle, and here's a rectangle. So what this delta x is saying, that is my delta x here is 2, but this could have been from 1 to 7, and then I can't, exactly visualize this as a whole number, right? We may need to do delta x 9 minus 1b minus a all over n, 4 rectangles, and we get 8 over 4, which is 2. But again, if it's not a whole number, we may need to rely on this rather than. Okay, so the left rectangle is saying start at your left endpoint, draw a rectangle to the next endpoint, start at your left endpoint where f of x is, draw a rectangle to your next rectangle, right, and keep going. Looking at this, we can see this is going to be an underestimation. I'm going to erase that there. Okay, the area of the graph, right, we're missing in between that parabola to the top of these rectangles here. So I know a left endpoint in this case is going to underestimate the actual area. Let's go ahead and work that math. I'll go and switch colors here. So for A, we're going to do a left. And rather than using that formula, let's break it down. I mean, a rectangle is base times height, right? And the base for each of these are 2. The height for 1 is 4, because I know if I plugged 1 into the function, 1 squared plus 3 is 4. Okay, the next spot we have here is 3. So we need f of 3, right? We need to see what that comes out to. 3 squared is 9 plus 3 is 12. Like I said, this is not to scale. I mean, it's pretty close, but don't worry if it doesn't line up. Okay, so this height was 12. The next one we know is 28. I did that one here, right? That's f of 5. F of 7. Substitute 7. We'd have 7 squared is 49 plus 3 is 52. So to do this area, I have 4 rectangles. I have 1 base. I'm going to say approximately, because we are estimating, right? We know it's an underestimate. So we have the base of 2, height of 4. The next one we have base of 2, height 12. Base 2, height 28. Base 2, height 52. Okay, so that's 8 plus 24 plus 56 plus 104, which comes out to be, let's see, that's 160, 184, 192. Okay, square, it didn't give units, but units, whatever, since it is area, right, units squared. Cool. Let's switch colors here. Purple's fine. Okay, now I want a right endpoint. Okay, so what's the difference? Well, blue and purple might contrast, so let's go and go like this ugly green here. Okay, now it's saying to use a right Riemann sum approximation. Go to your right endpoint, go up to f of x, and draw your rectangle to the left. Okay. Go from the right, the next endpoint, draw your rectangle to the left, and so forth. 4 of those. Notice the base in each of these is still 2. And notice with each of these I had 2 times the function, right? F of x1, f of x2, or f of 3, right? F of 5, f of 7. Well, now I have 2 times this f of 9, which we knew this height, right? This rectangle was 84 units high. Since the base in each of these is the same, another way we could do this is just factor that base out, right? We know it's 2. And then add all those heights. So The biggest rectangle had a height of 84, plus the next one at a height of 52, the next one at a height of 28, and the last one at a height of 12. Notice 3 of them were the same from above, right? But now we have this large end rectangle. Okay, so we get 2 times, let's see, that's 40, 92, 176. So 352 square units. That's our right approximation. Okay, the middle, be creative with this color. Pink should do, yeah. Okay. The middle then is saying, go from this middle of each, how do I say this, rectangle, right? So for instance, I'm going up from here and doing that rectangle. Okay, I'm going up from here and drawing a rectangle. Now notice, and I know this graph is getting a bit cluttered here, but now notice a piece of it, right? A piece of this is above the parabola, while a piece is below. While we are missing a piece, I should say, right? We're missing that piece, but we have that blue piece. We're missing that piece, but we have that. So it's almost like we hope they kind of cancel each other out and meet right in the middle. Alrighty. So C, we have a mid. Unfortunately, I need all new values, right? Because the height of these do not repeat from either the left or the right. So I need to do f of 8, I need f of 6, f of 4, f of 2. I'm going to go ahead and write that actually. We have delta x, which is still the base is 2 for each of these, right? But then I have f of 2 plus f of 4 plus f of 6 plus f of 8. So 2 squared plus 3, that is 7. 4 squared plus 3 is 19. 6 squared plus 3 is 39. And 8 squared plus 3 is 67. Okay, combine all these, that's 26, 56. 132 multiplied by 2. So we get 264 square units, which is kind of, I don't know if it's exactly in the middle without doing the math, but it is in the middle of the left and the right. And look how close that midpoint one was to the actual 266 and 2/3. That's a pretty good approximation. Okay, we could even take this step further. We're not going to do it in this class, but 2 things to branch off here. One is, let me draw this off to the side. If I had I'm going to draw a parabola once again. If I had a parabola, I could make this approximation even better by, instead of doing rectangles, doing trapezoids, because I'll just draw 2 here, right? Notice with 2 trapezoids, I'm almost following that curvature, right? So we could do trapezoids. It makes the formula uglier, but it is an even better approximation. The last thing I want to say is because in Calc 1 we learned all about limits and how they were used to find the slope of a tangent line of a graph, and then we kind of ignored them after that. This is in fact using limits when we do this definite integral and we get the when we get the exact area, because here's what's happening. Okay, no matter which rectangle you use, I don't care. I'll just split this up into 2 for now, right? I have 2 rectangles here, and whether I do left or right areas, I don't know. The idea is that we're going to make infinitely many rectangles within the bounds A and B here. Okay, infinitely many rectangles which are infinitely small, right, in width. So what do I mean by that? Well, say I did right rectangles. If I wanted to draw 100 in here, right, obviously I can't, but the more rectangles I have and the smaller the width, the better the approximation is going to be. So what we do is we take this width, which we call delta x, right? And we take that limit as that delta x goes to 0. And then n is the number of rectangles. We're taking the limit as n approaches infinity. I want infinitely many rectangles in here to where they're so thin, you're actually no longer approximating, you're getting a perfect area, right? That is our definite integral.